Good evening all. Last class we have seen inductance of a two-wire system. Today we shall see inductance of three-phase overhead transmission line. Consider three conductors A, B and C, each of radius R, of a three-phase transmission line carrying currents IA, IB and IC respectively, having spacing between them as DAB, DBC, DCA respectively. This is the diagram for arrangement of conductors A, B and C. Pistons are also shown in the diagram. Assume that the load is balanced. That means IA plus IB plus IC equal to 0. Then total flux linkage with conductor A, lambda A is equal to flux linkage with conductor A due to its own current IA plus flux linkages with conductor A due to current IB plus flux linkage with conductor A due to current IC. Substituting, we will be getting the expressions as mu 0 IA by 2 pi into 1 by 4 plus integral r to infinity dx by x plus mu 0 IB by 2 pi integral dAB to infinity dx by x plus mu 0 IC by 2 pi integral dCA to infinity dx by x. We can take mu 0 by 2 pi as a common term. So mu 0 by 2 pi into 1 by 4 plus integral r to infinity dx by x into IA plus IB into integral dAB to infinity dx by x plus IC into integral dCA to infinity dx by x. Now integrating and applying the limits, we are getting mu 0 by 2 pi into 1 by 4 plus log infinity minus log r into IA plus IB into log infinity minus log dAB plus IC into log infinity minus log DC. Now, again we can combine terms containing IA log infinity together, so that inside the bracket we will be getting it as IA plus IB plus X. This is, the expression becomes mu 0 by 2 pi into 1 by 4 minus log R into IA minus IB log DAB minus IC log DCA plus log infinity into IA plus IB plus IC. Now lambda A is equal to mu 0 by 2 pi into 1 by 4 minus log R into IA minus IB log DAB minus IC log DCA. Since IA plus IB plus IC equal to 0, the term containing log infinity becomes 0. Now we shall consider the conductors with symmetrical spacing. If the three conductors A, B and C are placed symmetrically at the corners of an equilateral triangle of side D, then DAB is equal to DBC equal to DCA equal to D. Under such a condition, the total flux linkages with conductor A is equal to lambda A, which is equal to mu 0 by 2 pi into 1 by 4 minus log R into IA minus IB log D minus IC log D. Now we can combine terms containing log D together, so that expression becomes mu 0 by 2 pi into 1 by 4 minus log R into IA minus IB plus IC into log D. Since IB plus IC equal to minus IA, it can be replaced in this expression. Mu 0 by 2 pi into 1 by 4 minus log R into IA minus IA log D instead of IB plus IC. Therefore, lambda A is equal to mu 0 IA by 2 pi into 1 by 4 minus 1 by 4 plus log D by R, combining the logarithmic terms together. This much Weber terms. Now we shall consider the inductance of conductor A, that is equal to LA given by lambda A by IA. Substituting for lambda A, the expression becomes mu 0 by 2 pi into 1 by 4 plus log D by R Henry per meter. Now mu 0 is equal to 2 pi, 4 pi into 10 raised to minus 7. Then divided by 2 pi into 1 by 4 plus log D by R. Now LA is equal to, rearranging the terms, we will be getting it as 10 raised to minus 7 into 1 by 2 plus 2 log D by R Henry per meter. This is for symmetrical distribution. Now we shall consider the unsymmetrical spacing. This will be the arrangement. So over one barrel of distance, the conductor A will be occupying positions 1, 2, 3, etc. Similarly, conductor C will be occupying positions 2, 3, etc. Similarly, B also. Okay. So over one barrel distance, all the conductors will be occupying positions 1, 2, 3 simultaneously. The conductor spacing in a three-phase transmission line is said to be unsymmetrical if the conductors are not equidistant from each other. Under such condition, the flux linkage and the inductance of each phase are not the same, and subsequently the voltage drop in three phases are unequal even if the currents in the conductor are balanced. In order to make the voltage drop equal in all conductors, we generally interchange the positions of the conductors at regular intervals along the line so that each conductor occupies the original position of every other conductor over an equal distance. Such an interchange of conductor positions is called transposition. Okay, this is called transposition. Conductors are changing their positions. The phase conductors are designed as A, B, and C, and positions occupied are numbered 1, 2, 3. This arrangement causes each conductor to have the same average inductance over the transposition cycle. Let us assume balanced conditions, that is IA equal to IB equal to IC equal to I in magnitude. Taking IA as the reference vector, the currents are represented as IA equal to I into 1 plus J0 in rectangular form. IB is equal to I into minus 0.5 minus J 0.866. IC equal to I into minus 0.5 plus J 0.866. Because all these currents are separated by 120-degree phase difference. So they are represented in their rectangular representations. As proved earlier, the total flux linkage per meter length of conductor A is lambda A is equal to mu0 by 2 pi into 1 by 4 log R into IA minus IB log DAB minus IC log DCA. Putting the values of IA, IB, IC, we get lambda A is equal to mu0 by 2 pi into 1 by 4 log R into I. IA represented as I. Now, substituting for IB and IC, we will be getting minus I into minus 0.5 minus J 0.866 log DAB minus I into minus 0.5 J plus 0.866 log DCA. Now, rearranging the terms, we will be getting it as mu0 by 2 pi into 1 by 4 I minus I log R plus 0.5 I log DAB plus J 0.866 I log DAB plus 0.5 I log DCA minus J 0.866 I log DCA. Therefore, it becomes mu0 by 2 pi into 1 by 4 I minus I log R plus 0.5 I log DAB plus J 0.866 I log DAB plus 0.5 I log DCA minus J 0.866 I log DCA. Again, rearranging the terms containing 0.5 I as well as J 0.866. We will be getting the next expression mu0 by 2 pi into 1 by 4 I minus I log R plus 0.5 I log DAB plus log DCA plus J 0.866 I into log DAB minus log DCA. That is equal to mu0 by 2 pi into 1 by 4 I minus I log R plus 0.5 I log DAB into DCA plus J 0.866 I log DAB by DCA. Now this becomes mu0 by 2 pi into 1 by 4 I minus I log R plus I log root of DAB into DCA plus J 0.866 I log DAB by DCA. This is equal to mu0 by 2 pi into 1 by 4 I plus I log root DAB DCA by R plus J 0.866 I log DAB by DCA. I can be taken out. So that mu0 I by 2 pi into 1 by 4 plus log root DAB DCA by R plus J 0.866 log DAB by DCA. Inductance of conductor A, LA, is equal to lambda A by IA, that is equal to lambda A by I. This is equal to mu0 by 2 pi into 1 by 4 plus log root DAB DCA by R plus 0.866 log DAB by DCA Henry per meter. Current will cancel out. Now we can substitute for mu 0 as 4 pi into 10 raised to minus 7. So it becomes 4 pi into 10 raised to minus 7 divided by 2 pi into 1 by 4 plus log root dAB by d. dAB dCA by R plus 0.866 log dAB by dCA Henry per meter. Now rearranging the terms. LA is equal to 10 raised to minus 7 into 1 by 2 plus 2 log root dAB dCA by R plus J 1.732 log dAB by dCA Henry per meter. Similarly, we can write the expression for LB and LC. Inductance of each line conductor is equal to 1 by 3 times LA plus LB plus LC. Substituting all this, we will be getting it as 10 raised to minus 7 into 1 by 2 plus 2 log cube root of dAB dBC dCA divided by. If the formula of inductance of an unsymmetrically spaced transposed line is composed with that of symmetrically placed line, we find that the inductance of each line conductor in the two cases will be equal if D is equal to cube root of dAB dBC dCA divided by R. The distance D is known as equivalent equilateral spacing for unsymmetrically transposed line. Okay, thank you very much. With this, we complete the inductance portion. The next class we shall see the capacitance. Thank you.